Behold, Beer's Law Lab. In today's episode, we'd like to find the unknown concentration of a mysterious solution. Hi, I'm Emily.
And I'm Isabel.
And we're from Mrs. Moore's AP Chemistry class.
Okay, to start with a little introduction. Now, when light is passed through a solution, some of this light is actually absorbed by the ions and molecules in the solution. Now, this principle is applied in a science known as spectrophotometry. So, the amount of light absorbance varies directly with the concentration of the solution and the length of the path that the light takes. This relationship is summarized in a law known as Beer's law.
So here's the formula. A is equal to ELC. So A is the absorbance, E is the molar absorptivity, C is the concentration, and L is the cell path length. So the cell path length is the length of the cuvette, as you can see in the diagram. And here's a beautiful cuvette.
So there are a couple purposes in this lab. First of all, we want to understand Beer's law and to implement it in an experimental setting. We'll be doing that by finding the concentration of an unknown cobalt chloride hexahydrate solution. And then we want to know how to use the spectroscopy machinery. Here's the beautiful solution.
So we hypothesized that through applying Beer's law, we will be able to accurately determine the molarity of an unknown solution.
So now to begin the experiment, first of all, we need to create a 0.1 molar solution of cobalt chloride hexahydrate. And we want to have 100 milliliters of this. So we use the molar mass of cobalt chloride hexahydrate and dimensional analysis to find out that 2.38 grams need to be added to a volumetric flask to make 100 milliliters.
Next, in order to create 4 other samples, we diluted our stock solution. So we took our 0.1 molar solution, diluted it with water to 0.08, 0.06, 0.04, and 0.02.
Okay, and then finally, now we want to collect some data. So first of all, we determined which wavelength would create the maximum absorbance for our stock solution. Then we measured the absorbance of all our solutions with this wavelength. And then finally, we measured the absorbance of the unknown solution.
So here's our data. So the general trend was that as we decreased with molarity, the absorbance also decreased as well. And our unknown was around 0.15.
So with these data values, now we can create a graph that shows our correlation between our absorbance and our concentration, and we can create lines of best fit to find correlation curves.
So using the equations that Isabel just described, we plugged in our values and we got our concentration to be around 0.0372 for the unknown solution.
So then now we want to look at percentage error, and for this we've used the average class data value as our accurate concentration, and we've used our average calculated value. And we find about an 8.05% difference between the two values.
So we also found the average was 0.0441 for our 4 trials, and also the standard deviation was very low at 0.00502.
So the average molarity of the class data was actually a little bit higher at 0.0477. The standard deviation was also relatively high, about 20% of the calculated value. There were 3 outliers in this data.
So for our results, our hypothesis was confirmed, and we were indeed able to apply the Beer's law in order to find the unknown concentration.
So we determined that this was a very robust method. It was repeatable and it produced relatively accurate results. There was some variability, especially between our individual group and that of the entire class, and that's due to a variety of reasons, inter-investigator variability, and possibly also the SPEC 20s.
So even though we tried to carry out the protocols to the best of our ability, there were definitely potential room for error. So first of all, there's the systematic error of using the pipettes where there could have been residual liquid left within the pipettes, and this would have lowered the concentration.
Then there were also accuracy limitations. We're trying to create solutions of exactly 0.1 molar and 0.08 molar, but that's not really possible. The volumetric flask itself might have a little bit less or a little bit more than 100 milliliters of water. The mass of cobalt chloride measured might not exactly be what's needed for a 0.1 molar. And then the pipette measurements, as we've discussed, can be slightly off.
And also, the hydrate may have not completely dissolved, and this would have led to a
decreased concentration.
Okay, also there may have also been residual water in the cuvettes and the tubes, and this would have led to a
decreased concentration.
And finally, there may have been smudges or fingerprints on the cuvettes, which would have made it difficult for the light to be transmitted through, and this would have been led to a
increased absorbance. So then, in conclusion, spectrometry is actually a very powerful method. Now, it relies on the physical principle of interactions between energy, in this case we use light, and mass, the particles in solution. The question does arise is whether this is a better method than titration in determining concentration. That would be interesting to look at, but this method also has a wide range of applications.
So for our future work, we'd like to compare using the Spec 20 that we used along with using titrations or nanodrop in order to determine the concentration. So in nanodrops, we do not need to use cuvettes. Also, we'd like to develop a method in order to clean cuvettes more thoroughly. Here are our references.
We want to thank Mrs. Ismore for teaching us what we need to know for this lab and for also watching over us while we conducted our experimentation.
Thank you for your time.